Okay, so today's the last lecture of the course, as you know. It's an extended lecture for two reasons. One is because I'm taking over part of the exercise class. I wanted to get two additional topics that are related to each other, as we'll see, somehow into the course for those who are prepared to hear it. So I wanted a little bit of extra time because of that. But also there was 1 week during the course where I cancelled the lecture because of illness. And then that meant I've also had a bit of time to make up. Part of that time had somehow already done in some sense by having the long day with you when you gave your presentations, which were an extra couple of hours, but so I still owed officially 1 more hour. So that's another reason why, an official reason why I've added an hour to today's lecture. Anyway, to make it, 4 hours of lecture is a long time. So to make it palatable, hopefully, things are going to be divided into 2 halves. So the first half is going to be from now, so that's 14 hours until, so 2 hours until 16 hours, and that's going to be on what's called algorithmic complexity theory. And I'll try to make this a short 2 hours, well, a short hour and 45 minutes with a short break in the middle, maybe not a 15-minute break. But then the idea is we'll have a longer break at the end of this, and then second block will start after a longer break. I mean, we have to see that things will go to plan, but anyway, then from 4 o'clock until 6 o'clock, we're going to look at, well, let me call it algorithmic randomness. Like these are 2 application areas of repeatability theory. One is to give some sensible notion of complexity to address an issue that I'm going to talk about in a moment, so I'll explain that in a moment. And another is to make sense of the notion of randomness. And the whole topic of what is randomness is a very interesting mathematical and philosophical topic. So we'll start with algorithmic complexity theory, and here the basic idea goes to Kolmogorov, the same Kolmogorov who was responsible for the development 100 years ago of modern probability theory. He did many things, and applications of computability theory were one of the things he did, and in particular, this idea of algorithmic complexity theory. The idea here, well, it sounds the same as computational complexity, just from the words. Algorithmics like computational, and there's a subject called computational complexity theory, but actually it's a distinct topic. What's called computational complexity theory in English is about looking at the computational problems and the algorithms that run them, and seeing how complex those algorithms are or problems are, in the sense of how much time or how much space resource or something like that we need to be able to compute it. What's called algorithmic complexity theory is a different kind of complexity theory. It's about how complex it is to describe something mathematically. So, for example, I might give you a description of like this, the first 1 billion digits in a binary expansion of pi. Or rather, I could say by digits, I mean binary digits. And we'll forget about the decimal place. So not the decimal place, the binary place. So it would start 1, 1 point, but we'll just start 1, 1 and then carry on like that. So this is a description of a binary string whose length is 1 billion. That's 10 to the power of 9. I'll give you another description of a binary sequence of length 1 billion, and that's 0, 1, 0, 1, 0, 1, 0, 1 repeated to 1 billion digits, bits. So the pattern by repeated is obvious what I mean. I mean the pattern of 0, 1 is repeated 500 million times. And another example of a sequence of 1 billion bits would be, suppose I'm tossing a coin, and it happens, this can be heads because it looks like a head, and tails because it looks like a tail. And I'm just tossing a coin, and this is just what happens to come up. I mean, I'm not actually doing it, and I'm not actually going to write out all 1 billion bits here, but I'm just going to say obtained by tossing a fair coin. So there are a few differences here. I mean, this third one is not a precise description of a single 1 billion digit, a single 1 billion bit word. But on the other hand, we could take it as, suppose we've actually tossed the coin 1 billion times. So let's pretend that we really do have a particular 1 billion bit word to hand here that we're referring to. The point I want to raise with you, and the kind of Kolmogorov's idea is, there's a clear hierarchy of complexity here in how difficult it is to describe these actual concrete sequences. So this one's the easiest to describe because we can give a very simple little algorithm that will compute this one, right? I mean, there's a tiny little Turing machine that will do this. The main difficult thing in the Turing machine is to implement the counter up to 1 billion to tell it when to stop. That's the hardest thing to do, but you can also that's not a difficult thing to do. So there's going to be a Turing machine with actually rather a few number of states that will implement this, rather simple one. This one here is, well, it's easy to describe in English, but that's because the English language is, well, natural language is quite developed, and more particularly mathematical culture is quite developed. If we wanted to understand this in more depth, of course, we really need to understand an algorithm for producing the binary digits of pi. Of course, such algorithms exist and are not that particularly hard to describe. They're a bit harder to describe than just repeating 0, 1. But there's a not too large Turing machine that will compute this binary string. On the other hand, this binary string that we obtained by tossing a coin 1 billion times, well, unless we were exceptionally, ridiculously lucky, which is really, really unlikely, this string, this word of 1 billion bits, is not very likely to have a simpler description than basically just listing the word itself. And the idea that Kolmogorov had was, well, we can use the notion of algorithm that I've already implicitly used in describing the complexity of these to actually define a notion of how complex a word is in terms of essentially how short the algorithm is that will produce that word. Every word has an algorithm that will produce it, but in the worst case, the algorithm is pretty much this is the word, and you list the word bit by bit in the algorithm. And this sort of these randomly generated sequences are very likely to end up in that worst case because they don't have any, they're very unlikely to have any pattern in them, like really ridiculously unlikely to have any pattern in them. So the idea of Kolmogorov complexity is to say, well, we'll assign a notion of complexity to a word, and the complexity is somehow the size of the Turing machine, of the smallest Turing machine that will generate that word. Okay, so let's actually make a definition out of that. Now we could do it using Turing machines and measuring their size, and it would turn out to be exactly equivalent to what I'm going to do. But by this stage in the course, it's more natural to work with more abstract mathematical entities, such as computable functions. And rather than a Turing machine, and rather than looking at Turing machines and considering the size of the Turing machine as the generating things, if we take a function, a computable function that's universal, similar to the universality property of a Turing machine, but universal meaning it is powerful enough to encode all computable functions within it, then we can take the size of the program, as it were, to be the length of the input string to the universal function. So just like when we have the universal Turing machine, that's one way of giving a natural size of a Turing machine, because we could define the size of a Turing machine to be the size, the length of the input string that we give to. That's a description of a Turing machine that we give as the input to the universal Turing machine. So with those ideas in the background, I'm going to define the relevant concepts. So we're going to work with functions. We're going to go back to the early days of the course and look at functions computing with computable functions computing on words. So a computable partial function on words. A note that I'm restricting to the binary alphabet here. Everything that I do could be done for any finite alphabet apart from well, it has to have at least two elements to make things work sensibly. In this case, we want the length of the string to be logarithmic in sort of the content of the string, so to speak. But fixing the binary alphabet turns out to be sort of a useful thing to do. And it's no loss of generality because, as I remarked in the early lectures, all Turing machines on finite alphabets can be reduced to Turing machines on the binary alphabet simply by coding the finite alphabet up using the binary alphabet. As a character in the finite alphabet becomes a word in the binary alphabet. Anyway, so a computable partial function on words is universal if this computable partial function subsumes every other computable partial function in the following way. So if for every other computable partial function F there exists a word p sub f which we view as a code for f, but we don't need to say how f is encoded, just the definition of a computable partial function, of a universal computable partial function, will constrain how b of f has to be encoded. So this this word BF needs to satisfy the following property, so such that in order that we can compute F on an input word W by computing the universal function on the input word W preceded by the prefix B sub F. So we simply what's the word for joining two strings to amalgamate those two strings, join the two strings together. We don't need to put a symbol between them. Now I was going to write equals here, but I would ask the question, what should I write instead of equals? But of course, by now, you know that the answer to that question is clearly equality, because these are partial functions. So this should be defined if and only if this is defined, and this needs to work for all input words W over the alphabet that we're looking at. So the point is, the universal function is in itself a computable partial function, but it computes any partial function by, it's like giving the encoding of a Turing machine. We give, as the start, as the prefix to the word, we give a word that is encoding in some sense the function F, and the universal function will decode that and then say, well, after I've received B sub F, I know what to do on W, and I'm going to, and I'll compute that as F. And by a construction, basically by the universal Turing machine construction, adapted from, we did the universal Turing machine for acceptance problems, but you can equally well do it for computing functions. Anyway, a simple construction like the universal Turing machine shows us that there exists a universal computable partial function. So a universal computable partial function exists. I'm just saying it is computed by a universal Turing machine, not the exact one that I described in the lectures, but a simple variant. By UTM, universal Turing machine. The nice thing about the definition of universal computable partial function is one only needs to know the notion of computable partial function, and from that, one doesn't need to worry about a particular encoding. The definition itself captures in a rather simple way all the properties we need. So we can now define Kolmogorov complexity. So as I said, the idea of the Kolmogorov complexity is somehow how complex the algorithm is that will give us, that will return as output the string that we're looking at the complexity of. Now we're going to use, instead of algorithm, and so how complex the Turing machine is, once we've got a universal computable function, well, we can view the input strings to the universal computable function as descriptions of, they contain, such an input string contains a description of an algorithm together with a description of the input we're giving it, essentially. It gets sort of parsed by the universal function in this way. And so if we're going to say, somehow here we have a description of the length of this composite stream. I'm sorry for the video because I already moved the camera, but and I see that we've gone out of focus as well. So the point is, this is a string. We kind of think we've got to hand a universal computable partial function. So that's sort of a model of computation, if you like, which will take our input seed that we give it and turn it into an output string. And we're going to then look at the length of these input seeds and see what the shortest input we can give is to get a particular output. So the Kolmogorov complexity of a word W, which is a word in binary alphabet, relative to a universal partial function function U, put that in brackets, is simply defined as, so we write K with Kolmogorov complexity relative to U of the word W, and it's simply the minimum length of seed we can give the universal function that will give us back W as an output. So the minimum over the, let me just check my notation in the notes just to be consistent. Minimum the length of all these such that U B equals W. Well, of course, B is a string binary symbols. So typically, you know, if we go back to our original examples, if we have a word like 0101001 repeated to 1 billion bits, well, somewhere, I mean, one of our computable functions is going to be the computable partial function that takes an input word, reads it as a binary representation of a number, and returns as output 0, 1, repeated however many times we gave it in the input. That's going to be some computable partial function. And that computable partial function, applied to the binary representation of 1 billion, is going to return this. It's going to return this string. You can imagine that, you know, it's quite likely that if we've done a natural encoding, the seed for that computable partial function, because it's rather simple, it's rather a simple program, is going to be a rather small string because it's not going to have to describe the Turing machine for it. Is going to have a relatively small description, so that will probably give rise to a relatively short string. So VF together with then the binary representation of a billion, well, that has log 2 of 1 billion roughly digits in it, which is whatever it is, but it's a much smaller number than, you know, it's a much smaller number than a billion. And so you can imagine that the Kolmogorov complexity is going to be relatively short. So it does depend on our choice of universal partial function, because we might have chosen a universal partial function that, for some perverse reason, gave a very long code to this particular function that iterates 0, 1 this many times. Okay, so the definition here is obviously relative to depends on a choice of universal partial function. But for natural choices, one expects it to behave in, to give sort of reasonable answers. On the other hand, in some sense, the choice, in a very important sense, the choice of universal partial function doesn't matter. And that's the first result about Kolmogorov complexity. We're given two universal partial functions. U and U prime, say. There exists a constant C such that for any word the difference between the Kolmogorov complexity relative to u prime and the Kolmogorov complexity relative to u of the word is always less than equal to C. So whatever your choice of universal partial functions, the Kolmogorov complexity differs by a constant, by mostly constant. Okay. So it's kind of rather a robust notion. We also write you might also write this as Ku prime of W is Ku of W plus the constant, where we're using this big O notation that's introduced in algorithm courses, although there are different ways of using this notation, and one of the ways of the best way of interpreting this is not exactly the same as the use of big O notation in an algorithms course. So I'm just saying people often use this notation. I'm going to comment with the notations that one often sees, but I don't want to spend time on mentioning that there are explaining the slight differences of what's meant here with an algorithms course. Well, or maybe to say with an algorithms course, when you write this, you normally mean an inequality. Here, I mean an equality, but the O1 can be a positive or a negative constant. Or I mean, sort of equalities bounded negatively, inequalities bounded negatively and positively. Anyway, the nice thing about this is we've got a sense in which Kolmogorov complexity, the precise numbers are not robust. The precise numbers depend on the choice of universal partial function, like if you like, the choice of the model of computation. But up to a constant, they agree with each other. Any two such notions agree with each other. So sort of constant related to complexity that are only associated to a constant, but only that aren't sensitive to a constant difference between notions. It doesn't matter on the choice of universal function. So I'm going to prove this. It's a very short proof, because it's actually very, very simple. So so the point is, if we've got two universal partial functions, u prime and u, because u prime is a computable function, there exists a seed for u, as I'm calling it, sorry, for u prime v sub u, such that u prime of w is the same as u computed on the feed v prime u prime to w, right? So u prime is a computable function, and u is universal, so the universal computable function computes. Also, u prime is one of the functions it computes as long as we give it the appropriate seed. And for the symmetric reason, u is also a universal function. So u prime is also a universal function. So there is the v prime, so a seed relative to the universal function u prime for the computable function u, such that so u of w, the function u, is computed by u prime on v prime of, sorry, this should be v prime of u prime. This is v prime, so this is v of u prime, this is v prime of u. This should be exist because there are two things. And this is basically the proof, because whenever we can compute a string using u, we can compute the same string using u prime by extending the string we gave as argument to u by a constant length v prime of u. And in the other direction, if we can compute a word uv x, if we can compute a word x as u prime of w, we can also compute that word from u by extending w again by just a constant number of symbols. But these two constants are just determined by u and u prime. So then this immediately follows, where if we take c to be the maximum of the maximum of the lengths of v u prime and u prime u. So the result follows with c is the max. The seed for u prime on the seed that the universal function u uses to compute the function u prime, and the seed that the universal function u prime uses to compute the function u. So this should be the maximum lengths of those strings. Okay. So given this is the robustness of the definition. So given this, we now henceforth choose a preferred universal function, partial function, but anyway, u, partial computable function u, and we write a w instead of a u of w. So we take this to be our preferred Kolmogorov complexity, but in any case, everything we do with it is going to be insensitive to additive differences, so it doesn't matter which preferred universal function we use. Okay, so how complex can the complexity of the string be? What's the worst case and what's the best case? Well, the best case is very short, because we might have made the encoding in such a way that the empty string is input. I mean, maybe we like the number pi so much that we actually tinkered about with our encoding so that on our universal function on the empty string computes the first billion binary digits of pi. So very complex string, very long strings can have very, very short inputs. So sort of lower bounds are, you know, there is no meaningful lower bound in some sense, but upper bounds we can give. So what's the worst case for the Kolmogorov complexity of a string? Any idea?
Just write out the entire string of the algorithm.
Right. So if you write out the entire string, then that's pretty much the worst case. Only we have to be a bit careful, because we can't say the worst case is the length of the string, but it's going to be the length of the string plus a constant. Yeah. But anyway, yeah, the idea is completely right. That's the worst thing, is writing down the whole string, which is what we're most likely to have to do for our randomly generated string. And actually, I mean, I keep on saying, unless we're ridiculously lucky. I should have just said at the beginning, in this case, we were imagining we actually did this a billion coin tosses, and in this case, we weren't ridiculously lucky. So we actually did get one that we needed to write in the whole string, and that was the best thing we could do. Might as well have just made that assumption at the start. Anyway, the upper bound we just discussed can be stated as a proposition So for any W, or so rather, there exists a C such that any W Kolmogorov complexity of W is less than or equal to the length of W plus the constant C. Or then A of W is less than or equal to length of W plus the constant. Point is the constant doesn't depend on W, it's just a universal constant. So the constant really depends on the choice of the universal partial function U. Right, I could write down a proof for this. But it's really very, very easy. The point is, so I won't write it down, I'll just tell you the proof. Point is the identity function on strings is computable. So there is some seed, V sub identity for the identity function. And then you will compute any string by giving it V of identity and following it by the string. So that's an upper bound for the Kolmogorov complexity of the string W, V of identity followed by W. So the length of the identity function, or maybe we will do the proof to this following for the following extent, which is we simply define C to be the length of the identity function. Okay, so that's an upper bound. And the idea is somehow, obviously, the smaller the complexity, the less complex you're viewing the string W. So when you get to the length of W as your complexity, we're now looking at strings that we're considering as complex strings, ones whose complexity, the length of seed we require to compute them is of the order of the length of the string. And so another simple proposition is that there do indeed exist strings of high complexity, and maybe the simplest statement to this effect, I think one can write more sophisticated statements, is there exist for any length n greater than or equal to 0, exist strings W of length n, so now we're looking at words of length n, such that the Kolmogorov complexity of W is greater than or equal to n. So there do exist complex strings where now Kolmogorov complexity means that my complexity is, complex string means my complexity is at least my length. Can anyone see a proof of this? It's a combinatorial proof, it's not.
You have so many words of this type, please, the most time you have on.
Yeah, you're saying the right sort of thing. So, so a universal function can there's only one word of length 0, so it has only one output for a seed of length 0. There are only 2 input words of length 1, so it has at most 2 outputs of for inputs of length 1, for any 4 words of length 2, and so on. So the number of possible different outputs for the universal functions on strings of length n is 1 plus 2 plus 4 plus 8 plus all the way up to plus 2 to the power of n minus 1 as the last number in that. Maybe 2 to the power of n minus 2. When 0 of length, the number of words with inputs of strings of length strictly less than n. Well, no, it's plus 2 to the power of n minus 1 at the end. And you sum those all up and you get 2 to the power of n all minus 1. So 1 less than 2 to the power of n. So you're left with one remaining string. And that remaining string can't have Kolmogorov complexity. Kolmogorov complexity less than n, so it must have Kolmogorov complexity greater than or equal to n. In fact, the situation is much better than that because universal functions are partial function, so there are many places in which it's not defined, and also it necessarily has repeated values as well. So in fact, there are many, you're going to get the same string occurring many times, but even if that didn't happen, you would be left with at least one string of complexity greater than or equal to n. Okay, so I said we're going to just have a short break in the middle of this, so maybe I want to do one last little definition. One of the concepts that one can make a good mathematical sense of using the concept of Kolmogorov complexity is the idea of data compression. In a sense, the Kolmogorov complexity represents the optimum data compression of the data of the word W. So you're thinking of W as an item of data, and its Kolmogorov complexity is like the smallest seed we can get for W. That's if we could data compress it in the best possible way. That's the length that it would have. But again, this data compression it's a little bit funny because it's got we're actually looking at the length of the seed, and the seed contains both a description of the model of computation together with the input in some sense. And the actual number itself is dependent on the choice of we're to clarify now that the choice of universal partial function. But still, you can see there's some concept related to data compression here. But we can't really make sense of it, use that to make sense for an individual string, because everything for an individual string depends on the choice of universal partial function. But an interesting thing to look at is the concept of an infinite string. And if we're given an infinite word, how complicated is the infinite word in the sense that do we have good ways of compressing the prefixes of the infinite word? So, for example, if we were given an infinite word 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, again the same thing. This is very, very compressible in the sense that every finite prefix of it is going to have a very short description. On the other hand, if we're given a randomly generated, not stopping now, bit sequence, so not stopping, but just an infinite randomly generated bit sequence, again, we're very, very unlikely to be able to compress the initial portions of this sequence. So Kolmogorov made the following definition. an omega word. So let's call it P because we were calling our omega words P typically. Infinite word is Kolmogorov incompressible if there exists a constant C such that for any length of prefix, if we look at the Kolmogorov complexity of the prefix, then it's basically as high as it can be. So we can't really compress the prefix. So as high as it can be means of the order of magnitude n. So the best seed for the prefix is basically the length of n. But again, we can't, we always have to deal with actual lengths with respect to an additive offset, depending on the spectral constant. So that's what our C is doing. So if there's some number C such that for any prefix at all of it, you can't encode it by a seed that's shorter than n just reduced by C. Okay. So again, people often write here, K P restricted to n, which is greater than equal to n minus O1 in this case. So this is a nice idea for an infinite sequence that's so nasty that you can't compress any, you can't in a significant way compress any prefix of it. And Kolmogorov thought this was a nice property that one should be able to prove that a randomly generated sequence enjoys this property, or is at least, with probability 1 going to enjoy this property. But actually this hope was dashed by somebody called Per Martin Love, who, those of you, if there are any in this room, I know at least one who are interested in, who know that there's something called the Martin Love theory of types, may be interested to know is the same Martin Love that invented Martin Love type theory. He also proved this result. And Martin Love, there does not exist, so there is no Kolmogorov incompressible sequence. So that's a kind of weird result to end on, because it's like the notion of Kolmogorov incompressibility looks like we're doing something interesting, but actually turns out that it doesn't make sense at all. But what I want to do in the next hour is show you that variants of these definitions, slightly more complicated, lead to a good theory of incompressibility. Right, so I'm going to pause the video now, and we're going to have a break. So it's 3:05. I said a short break, that can mean a 10-minute break, so we'll start again at 3:15. Okay, so what I want to do for this second part of the first hour is define a variant of Kolmogorov complexity, a variation on the idea due to Chaitin. I'm not quite sure how to pronounce the name. It resolves the problem with this definition of incompressibility. The idea here is we're going to consider a different notion of universal partial function now, which has the following difference, which is, so our partial functions before were partial functions on words, where you give a word as input and then you get it to compute. Giving a word as input actually, in a sense, gives a little bit more information than the digits of the word, because you give the digits of the word together with, to give a word as input, you also give essentially the return signal when you enter the input. You're basically saying, this is my input sequence, and I'm ending it at this point. So in a sense, there's an implicit sort of end of string terminator there. So in a sense, looking at the length of such sequences is a bit misleading because you're looking at the length of the sequence that does not include this termination. You know, there's a bit more information there. And so Chaitin actually realized that if you get rid of that difference, if you require the seed itself to contain its termination, to be self-delimiting, as he called it, then everything works out better. So how do you require things to be self-delimiting? Well, we look at functions which you give them inputs bit by bit, and they know when you've come, you know, they're self-delimiting, so they decide, after they've seen so much input, at some point they will decide that this is the end of the input and they will go off and compute. So any set of partial function will be defined on a set of strings that enjoys a property that any two different strings on which it's defined, neither one will be a prefix of the other. Okay, because when the function's decided to terminate the input sequence at one point, you can't give it a longer input sequence that starts in the same way. So a set of words, W, which is, so capital W now, which is a set of binary words. But it doesn't matter that it's the binary alphabet here, is prefix-free, this is the definition. If for any two distinct, so distinct means different, they're not equal to each other, W and W prime, so little w and little w prime in the word capital W, in the set capital W, neither of W or W prime is a prefix of the other. Remember, a prefix means W is a prefix of W prime, and the word W prime starts with the characters of the word W, and then potentially carries on afterwards after it gets beyond W. Is a prefix of the other. The partial function, such a function is necessarily partial. There are no total functions, well, there are no total functions with this property. A partial function f on words is also called prefix-free if its domain is prefix-free. So a partial function with this prefix-free property will have exactly this property that I said, that you can view yourself as giving it its argument word bit by bit, and when you get to a word in its domain, the partial function will go off and compute it. It decides for itself because it's the unique word that starts with that sequence that you've given it on which it's defined. By this prefix-free property, no shorter word or no longer word can also be in the domain. So then, a universal prefix-free function, this partial function, but let's not put too many words in, is a computable partial function, computable prefix-free partial function U of words, such that with the same property as before, such that for any other prefix-free computable partial function, compar dot function f 0 on binary words as before, there exists a seed for F word, oops, such that as before, F of the word W is computed by computing U on the seed, followed by the word W, again for all W in words, for all words W over the alphabet. And this is a harmonious definition in the following sense that because U is a prefix-free function, the only partial computable functions that can be computed this way, because we compute a function by giving a common prefix, any partial function f that is defined in this way is necessarily a prefix-free function. So it's fit to get the notion of prefix-freeness fit together with the same definition we had before of universal prefix-free, of universal functions. Okay, so it seems like a slightly fiddly property, but the motivation is kind of getting rid of this little bit of extra information that we're not accounting for. At least that's how I understand the motivation. I mean, I understand it at a high level. I've never really understood it exactly at a technical level that this definition really does that. But anyway, it's good as a motivating story. And having done that, oh, I still want to go over to the other board, back to the other board. We're going to define the variant of the Kolmogorov complexity, which is called prefix-free complexity. Of a word relative to a universal prefix-free is just defined as before, that the complexity, which I'm now going to use C for, relative to U of W, is again the minimum length of a generating sequence, generating word that will generate the word W when U is applied to it. So the definition is exactly as before. The only change is that we're getting the word W by applying the universal prefix-free function rather than an arbitrary universal function. So I'm using I use K for Kolmogorov. C here seems appropriate to me because this is due to, as I've already said, to Chaitin. I don't know how to pronounce, but I know how to write it. Chaitin. So it seems appropriate to use Chaitin. But actually, some textbooks I've got use C and K the other way around. So use C for Kolmogorov complexity and K for the Chaitin version. I don't know why, but maybe that's standard. Anyway, for this lecture, it doesn't matter if you use non-standard notation, I'm going to be self-consistent in the lecture. So anyway, the mild definition, the mild variation seemingly in the definition with this strange prefix property incorporated. And we again have the same property that, of course, this definition depends critically on the choice of the universal prefix-free function that you're using to make it. Of course, it does. But once again, any two choices are going to be the same up to an additive constant by exactly the same definition as before. So given two universal prefix-free partial functions, U and U prime, the prefix-free complexity relative to U prime, so prime that maybe wasn't very clear before, differs from the prefix-free complexity relative to U by less than the difference is bounded by a constant, and again, like that using big O notation. Okay. And again, we can look at how complex bounding the complexity of strings. But actually now, we don't have a simple result like this, that the complexity of a string is bounded above by the length of the string, because we can no longer use the identity function, because the identity function is not a prefix-free function. Obviously, it's defined on all strings, so it definitely doesn't have a prefix-free domain. And indeed, this doesn't hold as this property as stated here. And it's rather subtle to state the property that does hold. So what I'm going to suffice with is something much weaker than one can actually state. But it's a nice enough way of bounding the complexity, which is that for any d greater than or equal to 1, sorry, strictly greater than 1, not greater than equal, and I'm viewing this d as a 1 plus epsilon, basically, so a d very close to 1, but it holds for any d, however close we get it to 1, there exists a c such that the prefix-free complexity is less than or equal to d times w, t times the length of w plus c. And it's again a way of writing this using big O notation, well actually using a concept called little o, which is a sort of contrasting concept to big O, which is basically saying that you're linearly bounded above for any small 1 plus epsilon linear factor. So this can be written as dw is little o of the length of w. That doesn't really matter. What matters is this idea here that we can't bound above by the length of the string plus a constant, but for any multiplicative factor we can bound above by that. I'm not going to give the proof of this. I'll just tell you the idea for the proof of this, and as so I'll tell you the idea. So the idea is we want to find a prefix-free function that's going to compute the length of w. So essentially, we want to that's going to compute w. So essentially, we want to give it the string w together with some termination symbol in order to terminate the input to turn it into a prefix-free function. Now, it's not easy to find because w is any string over the alphabet 0, 1. It's not easy to find a termination symbol. So we can do that by, for example, taking the 16 different possible characters that we can encode using 4 bits, using 15 of them to represent the information of w, and using the other one, say 0, 0, 0, 0, as a termination symbol. And that then gives us a string that is a small multiplicative factor longer than the length of w. If we took 52 bits instead and used 51 characters together with a termination character, then the multiplicative factor would be much smaller. But on the other hand, we'd have a much bigger constant here. But nonetheless, that's kind of how the thing works. You can get better results by saying instead we encode a string we say how a string terminates by first encoding the length of the string and then just run the string in ordinary binary as it was, but we know how long it is. And that's a way of, that idea and iterations of it give us a way of improving this bound. Anyway, the point is we no longer have this simple bound, but nonetheless we have a bound that you don't differ much from the length of the string. The other proposition goes through exactly as before, for even stronger reasons. There do exist complex, in a sense, strings relative to prefix-free complexity. And once one gets to incompressibility, one simply modifies the definition. You get what's called prefix-free incompressibility. And we make exactly the same definition as before, but an omega word, so an infinite sequence, is Kolmogorov, is prefix-free incompressible. I should have underlined that before, because I should have underlined Kolmogorov incompressible before, because it was the concept being defined. But anyway, now we're prefix-free incompressible if there exists, again, some constant such that for all prefixes of for all finite prefixes of the infinite word, the prefix-free complexity is bounded below by the length of the word minus that constant. And now, instead of Martin Mott's result, we have Chaitin's result, or Chaitin's result, which is that prefix-free incompressible sequences exist. So there exist sequences that are complex in this sense that you cannot compress their prefixes. Now I want to give you an outline proof of this. So this is like the main content of this first hour. And before doing so, just a remark on what we're doing here, that the notion of incompressibility is a little bit less persuasive now, in some sense. We've somehow attached the definition of complexity to this prefix-free complexity to not allow ourselves to smuggle in a bit more information, namely the length of the input word, by having this termination symbol that we haven't given. We've attached the definition like that. On the other hand, we know our upper bound of complexity is not just the length of the word plus a constant. Well, I mean, as I said, one can improve this, but it's, a little bit bigger than the length of the word plus a constant. So here, a string that we're calling incompressible is potentially actually allowing us to do a little bit of compression in it, because the complexity of our words is actually not equal to n plus a constant, at worst. It's equal to a little bit more than n plus a constant, and we're allowed to get the complexity down to n. So we've given ourselves a bit more room for maneuver, and of course that room for maneuver is what allows these in prefix-free incompressible sequences to exist. So it's maybe not so surprising that given this space, we do get this. But what I want to do is now describe explicitly some such sequence and try, if time permits, to take you through the outline of the proof that it is prefix-free compressible. So, Chaitin's example, let's clean the board. Chaitin's example is actually quite a famous example in mathematics. It has a name, it's called omega, with a capital omega. And it's well known, sufficiently well known that popular science books have been written about it, or not maybe explicitly on just omega itself, but it just creeps into popular science books as a sort of sequence that's so hard to describe that because it's incompressible, it's very hard to describe any finite portion of the sequence. And people get excited about this, and so I think some people in Australia have been trying to work out the first 10 bits of this number, and then maybe up to about n equals 11 or something like that by now. The actual number itself depends on a choice of prefix-free universal function. So maybe I'll say a bit more about sort of interesting aspects of it later, but let's just give a definition. Well, let me define it. So omega is actually going to be a real number between 0 and 1, and it's simply take all words W in the domain of the universal prefix-free function U. Sorry, not a set, it's a number. It's the sum over all words W, that's supposed to be, in the domain of the universal prefix-free function U of 1 over 2, well, 2 to the minus length of W, so 1 over 2 to the power of W. Simply that. So what does this mean? Well, it's called the halting probability. This number is the probability that if you randomly generate an infinite sequence starting with zeros and ones, that you land in the domain, you at some point land in the domain of the prefix-free function. So at some point, you toss a finite sequence that's in the domain, and the prefix-free function will terminate. And it's like a halting probability because we imagine that our universal prefix-free function, we're running it on an input. We don't know how long the input is because the input's going to tell us, self-delimiting, that the prefix-free property, the input's going to tell us when it terminates. We toss the coin until perhaps at some point the machine, the universal prefix-free function says, okay, I've got my input, I'll go off and compute, and here's the value I'll give you back. And this is the probability that we get such a result if we toss a coin. So Chaitin calls this the halting probability. Now that's not an infinite sequence, that's a number. So I should say, well, why is this a number between 0 and 1? Well, that's because the domain is prefix-free. So if you have a prefix-free set of words and you make the sum over any prefix-free set, you always get a number between 0 and 1. That's called the Kraft inequality, Kraft with a K, but it's actually an obvious property because prefix-free, definition of a set of words being prefix-free, is the same thing as saying it's a set of words such that the intersection of the cylinders for the two words is empty. You've got any two distinct words, they have empty intersection. That's the same thing as the prefix-free property. So the prefix-free property says, if we take a look at all the words in the domain, what this is doing is the probability of a sequence of pair coin tosses landing in the cylinder set beginning with W. And because because the domain is a countable collection of disjoint cylinder sets, then the probability of landing in the domain is indeed the probability of, is indeed the sum of the probabilities. Anyway, so it's kind of, it's the Kraft inequality, but this is, so let me write that down. And in my view, it's an obvious property. And you think about it in this way. Right, so this is a number. It turns out, so I'm not going to prove this, It's not difficult, but omega is irrational. In fact, it's non-computable. And so because it's irrational, it's not a dyadic rational, and so it has a unique binary expansion. And that binary expansion is, all right, Pu, which is, sorry, P superscript omega, P superscript omega 0, P superscript omega 1, P superscript omega 2, etc., which satisfies the property that omega is the sum from I counting from 0 to infinity. Well, just the usual way of interpreting this as 0.P0, P1, P2 as binary digits, so that's Pi times 2 to the minus I plus 1. And theorem of Chaitin, we put it to the bottom. Really a bit squeezed, but change color. So Chaitin P. So the binary expansion of the halting probability is prefix-free. It's prefix-free and incompressible. So this is Chaitin's theorem. Right. So I do want to do a bit of work now, which is prove this, give you an outline proof of this result. The idea is that the halting this halting probability, it's remarkable that, so it's mathematically not too difficult to define sequence. I mean, you just need to choose this prefix-free, universal prefix-free function that gives us, that determines for us this halting property. But nonetheless, even though it's defined in a simple way, it turns out that the prefices of this sequence are very complex. They cannot be very much compressed. There's no way of the prefix-free complexities are bounded, essentially bounded by their length, bounded below by their length, modulo some additive offset. Right, so how are we going to prove this? Well, so what we're going to do is look at the notes. Yeah, good. So I'm going to start by showing what we can do in a computable way if we're given an input prefix of the halting probability. It turns out if we're given an input prefix of the halting gives us a lot of information. So we're going to define a computable function on binary words. such that on input, if we give the function a prefix of the halting probability as input, then so an n symbol prefix, an n bit prefix, an n is defined on that, and moreover, when it's defined, it gives us some answer, and the answer, the word it gives us, satisfies the property that its prefix-free complexity is greater than n. And this constant f is not going to be prefix-free computable, that doesn't matter, it's just a computable function on words. But the point is we can, in a computable way, use the first n bits of the halting probability to find, in a computable way, a word of complex, but of high complexity, namely whose prefix-free complexity is strictly greater than n. So this computable f behaves as follows. So I'm going to define it via an informal algorithm. So f behaves as follows. So what do I call its input? Yeah, so firstly, we have the domain of the universal prefix-free function is a prefix-free set of words. It's moreover, the domain is a semi-decidable set of words, because this is a part of a computable function. So, namely, we can simply semi-decide if a word is in the set by running the universal partial function on it and seeing if it terminates. So we've got a semi-decidable set of words here, and as in the lectures on semi-decidable and computable enumerability, any semi-decidable set of words can be given a computable enumeration. We have a computable function from natural numbers to those words. So let W0, W1, W2, etc. be a computable enumeration of the domain of the universal prefix-free function. So by computable enumeration, I simply mean a computable function from numbers to words, where 0 gets mapped to W0, 1 gets mapped to W1, 2 gets mapped to W2. And because, remember that semi-decidable or computably enumerable sets were exactly those that had computable enumerations, and moreover, if it was an infinite set, they had computable enumerations without repetitions. And because this is an infinite set, because this is a universal function, then we can assume this is a computable enumeration without repetitions. And then, if we give f an input string, so on input, and now I want to look again to see what I call the input string in the notes. Look to the wrong place. So on any input string, so I'm going to use P0 up to Pn-1. So this is an arbitrary input string, so I'm not superscripting these P's with omega, but in the end we're going to look at what it does on input strings that are prefixes of P omega. But at the moment I'm going to look at what it does on arbitrary input. searches for the smallest n, capital N, so it's an input of length n, an input of length little n, is searching for the smallest capital N, such that if we sum from 0 to n minus 1, one over 2 to the power of the length of each of the wi. So we're looking at the first n of these elements of the domain of, so we've got, so this is an infinite sequence that gives us the domain of U. We're looking at the first n elements of the domain of U, and we're computing the probability of an input sequence eventually becoming that word. In other words, what we're computing here is a finite subsum of this sum here, which is computing over here. And we look for such the smallest n, such that this is greater than equal to the number represented by the finite sequence here in binary. So in other words, the sum from I equals 0 to little n minus 1 of p sub I times 2 to the minus I plus 1. So we will try to find the smallest n for which this holds if such an n exists. And if it does, what it then does is it then returns the first word, W, that it can find, belonging to the set of binary words, such that U of W is defined, but U of W does not belong to the set of does not belong to the set of U applied to W0 up to U applied to W n all the way up to n minus 1. So here there are finitely many words, most n of them, which can be computed because all these words W are in the domain of U. And we look for the first in, maybe we've got some standard enumeration of all finite words, and we simply return the first word for which this holds. We can compute the finite set and check any word doesn't belong to it. Now there's a remark to make here which I thought about where to put it in the notes, and okay, I don't put it at this point. So this is the description of the function f by this algorithm. We're now going to see what it does. We want to see if it enjoys this property. So let's clear the other board. So I guess this part of the lecture is going to go on until 4:05. Not that much left to go. And then we're going to have the promised long break. Right, so we want to prove that f enjoys this property. So we need to look at what f does when given now an input prefix of which is a prefix of the holding probability. So consider f on input So we're now giving it some input prefix of length little n of the halting probability. So F searches for the smallest n such that when we add the weights associated with the where are the W's? Okay. When we add the weights here associated with the words from W0 to Wn, we get up to the we get up to or beyond the number represented by the input sequence. Well, because omega is defined as the sum of these weights of input sequences, and because the W0, W1, W2, etc. is an exhaustive enumeration of them, eventually, so we've got our input sequence is the actual bit sequence for the probability of omega, and when we add infinitely many of these, we get all the way up to omega. So eventually, we will cross the threshold, which is the threshold, which is the number just represented by the first n bits of omega. So by the definition of omega, and now I want to change the camera position. So by definition of omega, there exists n, and moreover, the sum of if we consider the sum of we consider the number represented by the n bits of the first n digit, the first n bits of the halting probability. So that's 2 to the minus I plus 1. Sum from I is 0 to n minus 1. That's greater than 0. Sorry, this I wanted to consider omega minus this value. So here we well, I've written this, which is true, but this doesn't involve capital M. Well, anyway, this is true, and there does exist an N, and this is true, so that's okay. And these are strict inequalities because omega is irrational, so it can't be 0 and it can't be exactly 2 to the minus n. Right, and we also have that. And we also have this inequality here. So this value lies between. So this value lies between. So we have sigma I equals 0. So the number from the prefix is less than the sum, is less than equal to the sum that we've got from I is 0 to n minus 1 weights from words. Actually, the length of Wi, and this is less than omega And this difference here, and we have the omega minus the sum from I naught to n minus 1, 2 to the minus wi, is less than by this, is less than 2 to the minus n. Okay, because it's squeezed between these two numbers. Okay, so these are the three useful properties. Sort of run them into each other. So now, by this sum here, we've got that any element, so by the export definition of omega, any element of the domain of U contributes a weight of 2 to the minus the length of W to omega, to the sum that's making up omega. And that means that because when we sum all the first n elements of the domain in our enumeration, we get to we're closer to omega than 2 to the minus little n. That means that, so by, let's call this red star, for any I greater than or equal to capital N, so for any element of the domain that's not in the n that we've summed to get very close to omega, it's clear that the length of Wi needs to be strictly greater than n, little n. Because if it were equal to little n or more, we've not included this in our partial sum, and when we included it, it would contribute 2 to the minus, to a number that's greater than or equal to 2 to the minus n. And that would take us, and we can't have such a number missing because we're less than 2 to the minus n away from omega. So for any I greater than or equal to n, we know that the length of Wi, we have that. The length of Wi is greater than or is greater than n. Because anything shorter would contribute to great a weight, would take us beyond the value of omega, which you can't do with anything part of the sum that leads up to omega. So that means so any V that does not belong to the set of U W0 up to U of Wi minus 1, sorry, capital N minus 1, enjoys the property that a prefix-free complexity is greater than n. Why is that? Because if we consider a V that's not in the universal function applied to these first n elements of the domain, well, it's computational, it's not computational complexity, it's prefix-free complexity is the length of the smallest string that the universal function applied to it will give us the value V back. But we know that no string that gives us the value V back is in the collection of string of the first n strings from W0 up to Wn minus 1. So any such string is of the form wi, where I is greater than n. And such strings always have length greater than n. So the shortest string must necessarily have length greater than n. And because our function f returns such a value, let's make it harmonious by turning it into v. Sorry, no, that's wrong. We're looking at a v. So I made a mistake here. The function should return, let me put the I've overshot my 5 pass mark. I'm sorry. And now the camera is. Sorry, the function was supposed to return the first string v that's outside this set. So we have the C of F of omega of P omega restricted to n. So the first n digits, the first n bits of P, the complexity of that is greater than n. Okay, we're nearly done. I just need to use one more board. Okay, so we now use a general lemma, which is actually a very easy lemma, which is by a lemma for any function f, given a computable function f, we have that the computational complexity of f of any string w, well, let's in this case make it the string that we're interested in, which is the first n bits of the of Chaitin's halting probability. The computational complexity of this can be no worse, sorry, not the computational complexity, the prefix-free complexity of this, can be no worse than the prefix-free complexity of the input string to the computational function plus a constant. And the reason for this is that when we've got the function, this is for all n, because we've got a function here that's converting that's a computable function on its input, we can get a description for the function applied to the input string. We can get a description for that by combining a description for the input string together with a description for the function. The function is fixed here, so that gives us a constant, and we can therefore bound the complexity by it can only be a constant worse than the complexity of the input string. So we've got two inequalities here. This first one and which I'll call star star, because we already have a star. Well, let's call it A, actually. And this one B. And when we put them together, we see that we get what we want, which is that we put them together and we take the C over to the other side, and we have that the prefix-free complexity of P that we restricted to N is bounded below, actually strictly, sorry, is bounded above by C by N minus C from A and B. Okay, that was obviously more technical than I'm feeling like today. So in any case, we've got there the notes, which actually need a little correction, which is why I got a bit flustered in the middle. The notes will be published online. But in any case, we now have the proof that this Chaitin's omega, its bit sequence is what? Prefix-free, incompressible. Okay, so it's 4:15. I promised you a long break. So actually, the way I'm going to do this is let's have a half-hour break. The next part, I'm going to make it less technical than this last bit. I don't think I can cope with things as technical as this today. So the next part I'm going to do Martin randomness. We'll start again at 4:45, and I'm basically going to do one session for maybe an hour, 4:45 to 5:45, and that will be that. So in any case, that's the first part. I also gave it a misleading title. I called it algorithmic complexity theory. It did seem a bit funny at the time, and then I made the distinction between algorithmic complexity theory and computational complexity theory. I don't know what got into my head when I was saying that. So the actual usual name for this is algorithmic information theory, not algorithmic complexity theory. So that's what should have been the title for this first half. And that compares with the contrast is with the information theory in the sense of Shannon, thank you, which is probabilistic-based information theory. This is information theory based on the amount of intrinsic information in a string in the sense of the difficulty of expressing that string in terms of an algorithm. Okay, that's the end of algorithmic information theory. We're having a half-hour break until 4:45. So if you're not coming back after the break, thank you for your attendance so far. If you are, I shall be glad to see you. So I'm going to